This is Lecture 6, Multivariate Regression. By the end of this lecture, you should be able to understand why it is important to add control variables to a regression, understand how to interpret a multivariate regression, know how to interpret an R-squared and adjusted R-squared in multivariate regression, and know how to calculate estimates from a multivariate regression. Before I move on to new material, I would like to review some material from the previous lecture. In the previous lectures, I showed you how to use a bivariate regression to determine whether one independent variable has a statistical impact on a dependent variable. Bivariate regression produces the following equation: dependent variable hat equals b hat times the independent variable plus a hat. B hat tells us the effect that the independent variable has on the dependent variable. If the independent variable has no discernible effect on the dependent variable, then B hat would be equal to 0. As the independent variable increases, the dependent variable stays the same. However, we expect the independent variable to have an effect on the dependent variable, so we don't expect the coefficient B hat to be 0. Based on our hypothesis, we expect it to be greater than 0 or less than 0. If we expect there to be a positive relationship between our independent and dependent variables, we expect that as the independent variable increases, the dependent variable increases. Hence, the coefficient B hat for this line should be greater than 0 or positive. If we expect there to be a negative relationship between our independent and dependent variables, we expect that as the independent variable increases, the dependent variable decreases. Hence, the coefficient B hat for this line should be less than 0 or negative. Now we are going to move on to discuss how we can use regression to analyze whether multiple independent variables have an effect on a dependent variable. In most cases, we don't expect only one independent variable to have an effect on a dependent variable. Instead, we expect multiple independent variables to have an effect on our dependent variable. When this is the case, we run a multivariate regression. It is called multivariate because we use multiple independent variables. Multivariate regression produces the following equation: dependent variable hat equals b hat 1 times the first independent variable plus b hat 2 times the second independent variable plus a hat plus e hat. Note that there is what we call a partial regression coefficient, or b hat, for each independent variable. And note that the subscripts tell us which b hat belongs to which independent variable. So b hat 1 belongs to independent variable 1 and b hat 2 belongs to independent variable 2. Each b hat tells us the effect of each independent variable on the dependent variable while taking into account the other independent variables. There are several reasons why we should control for other independent variables in our regression models. First, many different independent variables can affect a dependent variable. If we leave an important independent variable out of our model, we are leaving important information out of the model. If the model does not take into account that other information, it might think the other independent variables have a greater impact on the dependent variable or a lesser impact on the dependent variable. As a result, the b hats of the other independent variables might not reflect the true b hats for those variables. For example, let's say we are interested in figuring out what factors lead some voters to be more conservative than others. We think that income has a strong impact on conservativeness of voters. So let's say we ran a hypothetical bivariate regression with conservativeness as the dependent variable and income as the independent variable. The b hat for income turned out to be 0.06. Now, we could say that education also has an important impact on how conservative a voter is, but we did not include that in our bivariate regression. So, to take this new information into account, we add education to our model and run a multivariate regression. As you can see, the b hat for income gets bigger. Because we did not include education in our first model, we underestimated the effect that income has on conservativeness. Another reason we run multivariate regression is that it allows us to make better estimates of our dependent variable. Since we are including multiple independent variables, it allows us to take into account more factors that explain variation in our dependent variable, leading us to make better estimates of our dependent variable. And if we make better estimates of our dependent variable, that leads to a reduction in our errors, and since our estimates of the dependent variable for individual observations will be closer to the true values of the dependent variable for individual observations, our errors will be smaller. And a reduction in error leads to a higher R-square and adjusted R-square, meaning our models are explaining more of the variation in our dependent variable. Last, we also run multivariate regression because a significant coefficient in a bivariate regression does not mean the independent variable has an effect on the dependent variable. If the independent variable is related to the true causal independent variable, it will seem like there's a statistical relationship between the independent and dependent variable in a bivariate regression. However, the independent variable really doesn't have an effect on the dependent variable. It is the true causal variable that is driving the relationship, but we did not include the true causal variable in our bivariate regression. This phenomenon is known as a spurious relationship. Hence, we need to include more independent variables in our models just to make sure our results are not driven by spurious relationships. So let's say education has a true causal impact on conservativeness, but we don't know that. We just think income does. So we run a bivariate regression model with income as the only independent variable. And it turns out that income has a positive effect on conservativeness. But the only reason why income has a statistical impact is because education and income are correlated. In this case, income is acting as a proxy variable for education in the model. It may look like people with higher incomes are more conservative, but that is only because people with higher incomes are also more educated, and more educated people are conservative. If this is the case, when we run a multivariate regression model, income may become insignificant and education significant, meaning that education influences conservativeness, not income. Now, before I show you how to run a multivariate regression analysis in SPSS, I wanted to show you how the analysis is calculated. It's important to note that I won't have you actually calculate a multivariate regression because, as you can see, it is a complex calculation. I just wanted you to have a basic idea of what the math is doing. So in multivariate regression, you calculate the coefficients b hat for each independent variable separately. Each calculation takes into account variation in all of the independent variables, just in different ways based on which variable you are focusing on. So in calculating b hat for the first independent variable x1, you would take into account variations in the first independent variable and the second independent variable. This is similar to calculating b hat for the second independent variable. You also calculate the a hat separately. This calculation is similar to the calculation for a hat in a bivariate regression. And you calculate the significance test for each b hat and a hat separately. The significance tests in multivariate regression are the same as in bivariate regression, where you conduct a t-test for each b hat and a hat to determine if they are different from 0. Now I'm going to show you how to run a multivariate regression in SPSS. Consider the following hypotheses. As the average GNP of a country increases, the amount of resources that country devotes to defense spending increases. Hypothesis 2. Countries involved in a conflict will spend more on defense than countries not involved in a conflict. In both cases, defense spending is the dependent variable. It is measured in thousands of dollars. And we have two independent variables, G and P, in conflict. G and P is measured in thousands of dollars, and conflict is measured either as 0 or 1. 0 means a country is not involved in a conflict, 1 means a country is involved in a conflict. Running a multivariate regression analysis in SPSS is the same as running a bivariate regression in SPSS, except with more than one independent variable. So you do analyze regression linear, you put the appropriate dependent variable in the dependent variable box, and then you put all of the appropriate independent variables in the independent variable box. Then you click OK. This is what the output should look like. The first row tells you all the statistics associated with the constant a hat. The second row tells you the statistics associated with the first independent variable. In this case, it is G and P. And the third row tells you the statistics associated with the second independent variable. In this case, it is conflict. The B column tells you the values of A hat and B hat for each independent variable and for the constant. The SIG column tells you the results of the significance test for A hat and B hats. So the first thing you should do after running your multivariate regression is write out the equation. Recall the equation is dependent variable hat equals B hat times the first independent variable plus B hat times the second independent variable plus A hat. So applying this to our example, military spending hat equals $335.40 times GNP minus 567,163.63 times conflict plus 576,886.56. Recall that in bivariate regression, the regression line went through the coordinate mean of the independent variable, mean of the dependent variable. The same is true for multivariate regression. The regression line we just calculated passes through the coordinate mean of all the independent variables and the mean of the dependent variable. After you write out your equation, you need to interpret the significance test for the coefficients B hat. In this process, you examine each coefficient separately. Recall that when we interpret the B hat, we want to know if it is different from 0. If B hat is not different from 0, there is no relationship between our independent variable and dependent variable. As the independent variable changes, the dependent variable stays the same. If B hat is positively different from 0, as the independent variable increases, the dependent variable increases. If B hat is negatively different from 0, as the independent variable increases, the dependent variable decreases. So to show you how to interpret the significance test for B hat, I will use the multivariate regression analysis from early in the lecture. Recall our regression equation was military spending hat equals 335.40 times GNP minus 567,163.63 times conflict plus 576,886.56. So we want to know if 335.40 is different from 0, and we want to know if negative 567,163.63 is different from 0. Recall that these rows tell us the statistics associated with B hat for each independent variable. The B cell here tells you what B hat is. First, you should look at the sign of B hat. If it is not in the expected direction, then B hat is not significant and it is indistinguishable from 0. So let's say you expected the independent variable to have a positive effect on the dependent variable, but B hat was negative. Then your B hat is automatically insignificant. You do not have support for your argument. If your B hat is in the right direction, then move to the next steps. Okay, so the next step is to look at the results of the significance test for B hat and SPSS. The last column here tells you the sig value for each B hat. If the sig value is less than 0.002, then the coefficient is significant and different from 0 at the 0.001 level. If not, move on to the next step. If the sig value is less than 0.02, then the coefficient is significant and different from 0 at the 0.01 level. If not, move on to the next step. If the sig value is less than 0.10, then the coefficient is significant and different from 0 at the 0.05 level. In all of these cases, you have support for your argument. The only difference between these three levels of significance is if your significance test meets this criteria, then your results would be significant at the 99.9% level. If your significance test meets this criterion, then your results would be significant at the 99% level. And if your significance test met this criterion, then your results would be significant at the 95% level. Now move on. Let's say your sig value is greater than 0.10. That means your coefficient is not significant and is indistinguishable from 0. You do not have support for your hypothesis. An important note before I move on, anytime you see a sig value of 0.000, that is less than 0.002, so you have significance at the 0.001 level. So applying this exercise to our regression example, we expected GMP to have a positive effect on military spending. The B hat was positive, so we move on to the sig value. The sig value is less than 0.002, so the coefficient B hat is significant at the 0.001 level. Now moving on to conflict. We expected conflict to have a positive effect on military spending, yet the sign of B hat for conflict is negative, so the coefficient B hat is not significant, is indistinguishable from 0, so we do not have support for our hypothesis. If a coefficient B hat was insignificant, you cannot make any conclusions. You do not have support for your hypothesis. If the coefficient is significant, then you can interpret it. If it is significant, then you start by indicating what level the coefficient is significant at. You indicate if the variable has a positive or negative effect on the dependent variable, all else equal. All else equal is just a very concise way of saying that you have taken into account the effect of other independent variables in your model, and even after doing that, this independent variable seems to have a statistical impact on your dependent variable. So going back to our example, when interpreting our coefficient for GMP, we would say the coefficient for GMP is positive and significant at the 0.001 level. All else equal, as GNP increases, military spending increases. Now moving on to interpreting the constant A hat. Recall that A hat is also the y-intercept. In this equation, it is 576,886.56. Interpreting A hat in a multivariate regression is similar to interpreting it in a bivariate regression. We do not have an expectation about whether A hat is positively or negatively different from 0, so we just assess whether it is positively or negatively different from 0. So to determine whether A hat is different from 0, we look at the sig cell here for A hat. Then we compare the sig value to these rules. Note that these rules are different from the rules for determining if B hat is significant. If the sig value is less than 0.001, then the constant is significant and different from 0 at the 0.001 level. If not, move on to the next step. If the sig value is less than 0.01, then the constant is significant and different from 0 at the 0.01 level. If not, move on to the next step. If the sig value is less than 0.05, then the constant is significant and different from 0 at the 0.05 level. If not, then the constant is not significant and is indistinguishable from 0. Also note that anytime you see a sig value of 0.000, then it is less than 0.001, and the significance is at the 0.001 level. Applying this to our example, the sig value for the constant was not less than 0.05, so the constant is insignificant. It is not different from 0. If it were significant, we would say that it is significantly different from 0. We would also note at what level it is significant and whether it was positive or negative. Now on to interpreting the R-squared in multivariate regression. It is almost the same calculation as in bivariate regression. The only difference is now that we have multiple independent variables in our models. Recall that an R-square of 1 means that our model perfectly estimates our dependent variable, and an R-square of 0 means our model cannot estimate our dependent variable at all. Now I'm going to show you how to interpret the R-square in multivariate regression. Suppose our R-square was 0.12. We would move the decimal place over to the right twice and treat the value as a percentage. So in this case, we would move the decimal place over twice and get 12%. Then we would say that variation in all of the independent variables explains R-squared percentage variation in the dependent variable. Or in this case, we would say variation in GDP and variation in conflict explains 12% of variation in military spending. The adjusted R-square in multivariate regression is also similar to the adjusted R-square in bivariate regression. Recall that the adjusted R-square takes into account the sample size and number of independent variables into account. Now I'm going to show you how to interpret the adjusted R-square in multivariate regression. Suppose our adjusted R-square was 0.11. We would move the decimal place over to the right twice and treat the value as a percentage. So in this case, we would move the decimal place over twice and get 11%. Then we would say that after taking into account sample size and the number of independent variables, variation in all the independent variables explains adjusted R-squared percentage variation in the dependent variable. Or in this case, we would say, after taking into account sample size and the number of independent variables, variation in GNP and variation in conflict explains 11% of the variation in military spending. Now I'm going to show you how to calculate estimates in multivariate regression. When you calculate estimates, you make predictions of the dependent variable. The first step in doing this is writing out your entire regression equation. Dependent variable hat equals b hat 1 times the first independent variable plus b hat 2 times the second independent variable plus a hat. Then you insert values into the equation for each independent variable. You should make sure these values make sense given your data. For example, often we want to know what the estimate of the dependent variable is when all the independent variables are at their means. So we calculate the means of the independent variables and insert them into the equation. We could also make estimates for when the independent variables are at their minimums or at their maximums. However, we should never make estimates for values of the independent variables that are outside the bounds of the data we have for our variables. So for example, if the maximum value for our first independent variable was 10, we would not make estimates for when the variable had a value of 11. So as an example, I will use the regression equation from earlier in the lecture. I wrote down the regression equation. Military spending hat equals 335.40 times GNP minus 567,163.63 times conflict plus 576,886.56. Let's say the mean of GNP was 20,000 and the mean of conflict was 0.5. I insert these values into my equation. Military spending hat equals 335.40 times 20,000 minus 567,163.63 times 0.5 plus 576,886.56. And the answer is 7,001,304,745. To interpret this information, you would say what values the independent variables are at and what the estimate is. So in this case, you would say when a country has an average GNP and conflict is at its average, that country should spend an estimated 7,001,304.745 on military spending.